When a spacecraft returns from lunar distance, it hits the Earth's atmosphere at approximately 25,000 miles per hour, roughly 11 kilometers per second. At those velocities, the vacuum of deep space is abruptly replaced by the dense particles of the Earth's upper atmosphere, converting immense kinetic energy directly into friction. That friction generates extreme heat, bathing the leading edge of the spacecraft in plasma approaching 5,000 degrees Fahrenheit. This cross-section shows Orion's primary defense, a thermal protection system utilizing an ablative resin-coated silica material known as AVCOAT. This protective layer, positioned directly between the crew cabin and the superheated plasma, is only a few centimeters thick. The 4 astronauts on board rely entirely on this single, non-redundant system. There is no backup heat shield. While the mission involves a complex 10-day lunar flyby, its success is ultimately bottlenecked by this final 5-minute thermal window. The uncrewed Artemis I test flight in 2022 provided engineers with their first look at how the Orion hardware handled that exact re-entry environment. Post-flight inspection data revealed unexpected structural anomalies across the shield's surface, as shown in this topographical mapping of the damage. Instead of burning away smoothly as designed, the AVCOAT material exhibited localized char loss, with chunks of the resin cracking and spalling off during descent. This presented an immediate constraint. The capsule for the crewed Artemis II mission, named Integrity, was already manufactured and its thermal protection system was fully installed. Physically tearing off and redesigning the heat shield would have compromised the vehicle's existing structural margins and forced a multi-year delay to the launch timeline. To protect the Artemis II crew, NASA systems engineers had to find a way to save the existing hardware using orbital mechanics, then validate that fix with live sensor telemetry. When critical hardware is locked in, the flight profile itself must become the engineering patch. This altitude versus time graph maps the aerodynamic skip re-entry profile used during the Artemis I flight. The capsule dips into the atmosphere, bounces slightly upward, and then descends for final splashdown. The maneuver is designed to bleed off excess velocity in the upper atmosphere, lowering the deceleration g-forces placed on the vehicle and the crew. However, this trajectory subjects the spacecraft to a cycle: intense heating during the initial dip, active cooling during the skip, and reheating during the final plunge. To understand why this matters, we must look at the molecular composition of the AVCOAT resin during that cycle. The manufacturing process of the resin leaves microscopic pockets of trapped gases suspended within the solid material. During the cooling phase of the skip maneuver, the outer layer of the shield drops in temperature. This shifting thermal gradient hardens the exterior, trapping those gases tightly inside the resin matrix. During the secondary reheating phase, the temperature spikes again. The trapped gases react to the extreme heat, rapidly expanding inside a newly hardened shell. The outward pressure of the expanding gas exceeds the tensile strength of the AVCOAT, violently rupturing the surrounding material and causing the jagged spalling observed on Artemis I. An aerodynamic maneuver executed to increase physical comfort ended up compromising the shield's internal thermodynamics. This brings us to NASA's software-based fix. This graph compares the original skip profile to the new Artemis II direct re-entry trajectory. The direct approach features a much steeper angle of descent, cutting through the atmosphere in a single, aggressive line. By plunging steeper, the spacecraft drastically reduces the total duration it spends in the upper atmosphere. This requires a major engineering trade-off. The capsule will experience a significantly higher peak temperature during its descent. It also requires the human crew to endure a sharper spike in deceleration g-forces, as velocity is scrubbed off in less time. The thermodynamic payoff for these trades is a single continuous descent. By eliminating the cooling cycle entirely, the heat shield never forms the hardened outer shell that traps the expanding internal gases. Under constant, continuous thermal pressure, the gases vent naturally, and the resin is predicted to ablate uniformly rather than fracturing from within. Systems engineers deliberately traded aerodynamic comfort for thermodynamic survival. But modeling a software fix in a computer simulation is only the first step. The direct re-entry profile must be proven empirically under actual flight conditions. This schematic displays the thermal protection system sensor network embedded across the base of the Orion capsule. These nodes gather real-time data, recording microsecond thermal responses across the ablative material as it burns away. Specific sensors are positioned directly at the AV coat block seams, constantly measuring heat flux to ensure the structural boundaries hold under peak thermal loads. Additional sensors monitor the areas downstream of the compression pads, tracking the heat flow vectors to detect any unexpected thermal channeling. As the capsule plummets, this telemetry calculates both the external heat load and the internal thermal gradients moving through the capsule structure. These sensor readouts provide the exact empirical data required to prove the direct trajectory successfully maintained the vehicle's structural margins at 25,000 miles per hour. The data collection culminates during the re-entry plasma blackout, the most critical and isolated phase of the entire descent. As the capsule hits peak friction, the superheated plasma wrapping around the hull physically blocks all radio frequency signals from reaching the Earth. During this window, there are no abort options, no manual overrides, and no backup plans. The physics of the direct trajectory must execute flawlessly. Once Orion slows down and clears the plasma field, Mission Control instantly reacquires the signal, and the backlog of TPS sensor data floods into Houston. This telemetry provides the first empirical record of deep space thermal loads, validating the hardware for the current mission and all future lunar returns. This split view illustrates how the live telemetry from Artemis II serves as the empirical baseline for predictive thermodynamic models on completely different spacecraft. Future vehicles returning from Mars will hit the Earth's atmosphere at even higher velocities, subjecting their shields to significantly harsher thermal limits. By recording exactly how ablative materials behave under continuous peak thermal loads, Artemis II secures the thermodynamic foundation for all future human interplanetary exploration.